Good morning, all of you. Myself, DrShrutiPatle, and I am here to present my work, Impact of Organic Molecule Lysine on Growth and Physiochemical Investigation in Ammonium Dihydrogen Phosphate Single Crystal. Now, the content of my presentations are Introduction to NLO Crystal, Growth of Pure and Lysine Doped ATP Single Crystal, Various Characterization, Result and Discussion, Conclusion, and Future Scope. Now, the nonlinear optical materials are nothing but the materials which which responds nonlinearly to the light, especially intense light. That's why we can say that nonlinear optics is the optics of intense light like laser. Now, in nonlinear optical material, the dielectric polarization responds nonlinearly to the electric field of the light, and especially the crystal, those lacking inversion symmetry, can exhibit this nonlinear behavior. And this nonlinear behavior of the crystals or the material facilitate us to manipulate the light or to change the frequency of the incoming light. There are so many phenomena are associated with the nonlinear application, and so many applications are there for the nonlinear optical single crystals. Now, here I am growing the ADP single crystal, which is doped with the L-lysine, and L-lysine, we know that it is an amino acid that is a very popular organic material, and whereas ADP is an inorganic material. So I am adding the organic L-lysine in a inorganic ADP material, because I want to combine the advantage of both ADP as well as L-lysine. Because in inorganic material like ADP, they possess following properties like high mechanical strength, high degree of chemical inertness, large size can be grown, but they offers very low in NLO coefficient. Whereas in organic like L-lysine, they possess large NLO coefficient, but they are highly sensitive, short response time, low mechanical strength, and bulk size crystal cannot be grown very easily. That's why I'm doping this L-lysine, organic L-lysine, in a inorganic ADP, so that a good quality crystal for application can be grown. And this class of combination of organic and inorganic can be called as a semi-organic material. Now, growing crystal, to grow a bulk size crystal, I have chosen the SR method. This is the setup of SR method in which from the small seed, the large size crystal can be grown by the solution. Just by maintaining the temperature gradient, we can get the bulk size growth, and that growth can be observed easily, and we can record the per day growth of our crystal. So in this method, we'll not go in detail due to lack of time. In this method, from the small piece of crystal, the large size crystal can be grown. These are the seed crystal, that is small crystals, of which I have grown the bulk crystal of L-lysine and the pure ADP. And this is the setup I have used to grow my crystals. And this is my crystal. Here we can see that from this portion to this portion, crystal shows the high transmission. It means this portion of crystal is very good, and I have sent this portion for the further characterization. So I did these following characterizations like single crystal XRD, powder XRD, FTIR, EDAX, thermal analysis, UV transmission study, micro hardness test, and SHG study. So starting with the single crystal XRD, here I got this data from the study, and by observing this data, we can say that our crystal belongs to the tetragonal symmetry. Here, all the crystal belongs to tetragonal symmetry. Only the slight variation in lattice parameter is observed. We can say that here, by comparing the volume of all these crystal, we can say that as by doping of L-lysine, the crystal symmetry is contracting, or its volume is decreasing. That means we can say that our lattice become more and more packed due to the addition of impurity like L-lysine. Now again, here I have compared the difference of side A and C of our crystal lattice. I observed that this difference is decreasing as we increase the concentration of L-lysine. So we can say that by doping of L-lysine, due to doping of L-lysine, our tetragonal symmetry is shifting towards the cubical symmetry. But up to the 1% lysine doping, it is tetragonal only. Hence, no change in structure observed at. If we increase the doping, so there may be chances that it will change the symmetry. Again, I have done the powder XRD analysis. In powder XRD analysis, we can see that all the graphs of all these three crystals, and here we notice that there is no additional peak is observed. Hence, we can say that up to 1% of lysine doping, the structure remains same. And these are the lattice parameter obtained from this study. And again, we can notice here there is a decrease in volume of the lattice of the doped crystal, hence increase in density of the doped crystal. Now, the next I have done the EDAX analysis. EDAX analysis is to investigate whether this organic L-lysine molecule is entered in our lattice of ADPs or not. So here this presence of carbon atom confirms the incorporation of L-lysine molecule in our ADP crystal. Now next I have done FTIR. In FTIR, if we compare all these three curves are almost same. Only some additional peaks are observed in the lysine doped ADP. And if we see the data which is tabulated here, these peaks are shifted towards the higher frequency side. Slight shift is there. That is again due to the presence of L-lysine. So here this FTIR also confirms the incorporation of L-lysine molecule within the crystal lattice of ADP. Now, next is thermal study. So in order to study thermal behavior of our all three grown crystals, TGA and DTA I have done. So from TGA curve, if we compare the TGA curve for all these three crystals, what I have observed that actually I have done this study from room temperature to 600 degrees Celsius, and what I observed that first decomposition start here around 200 degrees Celsius, that is actually at 195 degrees Celsius, and it is almost same for all three crystal. And this first decomposition is due to the dehydration of water molecule, and then steady decrease of weight is observed here, and up to 60% of weight loss is observed at around 500 degrees Celsius. And after that, there is a fast decrease of weight here, that is weight loss of around 80% is observed here, and we can say that at 600 degrees Celsius final decomposition of the material occurs. Now examine DTA curve. Now through DTA curve, if we observe for all these three of the grown crystal, this green curve is for 1% lysine, red one is for 0.5, and the black one for pure ADP. The sharp endothermic peak is observed, which corresponds to melting of the crystal. So if we see it clearly here, so this 1% lysine doped ADP has melting point around 200 degrees Celsius, that is exactly at 203 degrees Celsius, whereas this 0.5 has at 207 degrees Celsius, and pure ADP is having 215 degrees Celsius. All this data is tabulated here, and hence this confirms that the thermal stability of crystal decreases due to presence of L-lysine molecule in the crystal lattice of ADP. Now, moving towards the UV visible spectrum of the grown crystal, it shows that the crystal shows the transmissions from 200 nanometer to 1000 nanometer up to 1000 nanometer. This shows that our crystals offers good transmissions in all UV visible and infrared region. Hence our crystals are good for optical applications. Even again we can note that here the doping of L-lysine increases the transmittance of the crystal also. So from this data tabulated here, we can note down the pure ADP possesses 66% of transmissions, where 1% lysine doped ADP offers 82% of transmittance. That is really good enough. for the optical studies. Now, optical applications. Now, moving towards the micro hardness test. So, if you are talking about the device application, mechanical strength is a very important parameter to study. So that's why I've done micro hardness test. I have used Vickers micro hardness technique to find out the micro hardness of my grown crystals. So this graph shows that the 1% lysine doped ADP has the good mechanical strength as compared to the pure ADP. Now, moving towards the next very important characteristic, that is second harmonic generation. This SHG efficiency, SHG study confirms the NLO behavior of the material, and in this study we have subjected the powder of our grown crystal to 1064 nanometer wavelength, and the emerging wavelength was of green color, that is of 530 nanometer. That confirms the doubling of the frequency, we can say that, and hence this also confirms the SHG efficiency, that is we can say that NLO behavior of the grown crystal. If we compare the NLO behavior, that is SHG efficiency of our doped crystals with the pure ADP, we found that the 1% lysine doped ADP has the highest NLO coefficient, that is 1.53 times of that of pure ATP. So here I have done with all the properties. Now concluding, all the crystal belongs to tetragonal system, and EDAX and FDR confirms the presence of L-lysine, that is impurity, in our ADP crystal. Here TGA-DTA thermal analysis shows the decrease of thermal stability of ADP crystal due to doping, and UV visible spectra confirms the sufficient transmission in visible range, and doping enhances the transmission of our ADP crystal. The micro hardness test confirms the increase of mechanical strength of ADP due to the doping, and SHG efficiency also measured, and this also shows that its SHG efficiency, that is NLO coefficient, increases due to the presence of L-lysine in the ADP crystal. Now, comparing all these three crystals for the device application, we can say that the 1% lysine doped ATP is the best for device application in electro-optics industry, because it possesses good transmission, have higher mechanical strength, and good NLO coefficient if the thermal stability is not the point of concern. So thank you so much. Thank you for giving the chance to present my work here. Thank you. Thank you so much.